Understanding elliptical versus spiral galaxy formation. Look at a deep space image showing dozens or hundreds of galaxies, and you'll immediately notice diversity. Some galaxies appear as elegant spirals with sweeping arms and bright disks. Others look like smooth, featureless ellipses, red or yellow blobs without structure. Still others fall somewhere in between. These different morphologies aren't just cosmetic variations, they reflect fundamentally different formation histories, different evolutionary pathways, and different physical processes. Understanding why some galaxies become spirals while others become ellipticals is one of the central questions in galaxy formation and evolution. Today, we're exploring how these two major galaxy types form, what physical processes create their distinct structures, why spirals have ongoing star formation while ellipticals are mostly dead, and how galaxies can transform from one type to another. This is the story of cosmic architecture, how the diverse structures we observe today emerged from the relatively uniform early universe. Let's unravel the formation paths of elliptical and spiral galaxies. Defining the galaxy types. Before exploring formation, let's establish what distinguishes elliptical and spiral galaxies. Spiral galaxies are disk-dominated systems. They have flat, rotating disks containing stars, gas, and dust. Most display spiral arm patterns, density waves where material concentrates. They have modest central bulges and often bars. Star formation is ongoing, concentrated in the disk, especially in spiral arms. Colors are typically blue or blue-white due to young, hot stars. Gas and dust are abundant, providing fuel for continued star formation. Elliptical galaxies are spheroidal systems without disks. They range from nearly spherical to highly elongated ellipsoids. They lack spiral arms, disks, or organized structure, just smooth distributions of stars. Star formation has essentially ceased. Colors are red or yellow because they contain only old, cool stars. Gas and dust are scarce, having been exhausted or removed. There's also an intermediate category, lenticular galaxies, S0 type. These have disks like spirals but lack spiral arms and active star formation. They're transitional objects between spirals and ellipticals. Edwin Hubble's tuning fork diagram, created in the 1920s, organized these types. The handle of the tuning fork contains ellipticals, classified E0, spherical, through E7, highly elongated. The fork splits into two prongs, one for normal spirals, SA, SB, SC, and one for barred spirals, SBA, SBB, SBC. Lenticulars sit at the junction. Hubble thought this diagram might represent an evolutionary sequence, ellipticals evolving into spirals, or vice versa. We now know this is incorrect. The diagram organizes morphology but doesn't represent a simple evolutionary track. Both ellipticals and spirals form early in cosmic history, and transformation between types occurs through specific processes, not smooth evolution along Hubble's sequence. Modern surveys reveal these types' prevalence. In the nearby universe, spirals make up about 60% of large galaxies, ellipticals about 20%, and lenticulars about 20%. However, these fractions were different in the past and vary with environment. In galaxy clusters, ellipticals and lenticulars dominate. In the field, regions far from dense clusters, spirals dominate. Understanding why some galaxies become spirals and others become ellipticals requires understanding the physical processes that shape galactic structure. The early universe, starting conditions. Both ellipticals and spirals begin from the same cosmic ingredients in the early universe. Shortly after the Big Bang, matter was distributed nearly uniformly, with tiny quantum fluctuations creating regions slightly denser or less dense than average, variations of about 1 part in 100,000. These fluctuations, stretched to cosmic scales by cosmic inflation, became the seeds for all structure. Dark matter, being immune to radiation pressure and not interacting electromagnetically, collapsed first into gravitationally bound halos. Normal matter, hydrogen and helium gas, fell into these dark matter wells. As gas accumulated, it could lose energy through radiation and settle into denser concentrations. This is where paths diverge. The question is, why does some gas form disks while other gas form spheroids? The answer involves angular momentum, rotation. All regions of the universe have some net rotation acquired from tidal torques during structure formation. As matter collapses, conservation of angular momentum causes it to spin faster, just as figure skaters spin faster when pulling in their arms. If gas has significant angular momentum and can cool efficiently, it settles into a rotationally supported disk, a flat structure where centrifugal force from rotation balances gravity's inward pull. This creates spiral galaxies. If gas has low angular momentum, or if it can't cool efficiently and settle into a disk, or if violent processes disrupt disk formation, the result is a spheroidal system, an elliptical galaxy. The key factors determining which path occurs are angular momentum content, gas cooling efficiency, the timing and violence of major mergers, and environment. Let's explore each path in detail. Spiral galaxy formation, the disk assembly path. Spiral galaxies form primarily through relatively gentle, gas-rich processes that preserve angular momentum and allow disk formation. The standard model for spiral galaxy formation is hierarchical assembly through cold flows. Dark matter halos form first, merging and growing over time. Gas flows along filaments in the cosmic web, long chains of matter connecting dense regions, channeling gas toward dark matter halos. In the early universe, when gas was denser, these flows could reach the central regions of dark matter halos relatively undisturbed. The gas is cold in the sense that it hasn't been shock heated to very high temperatures. This cold gas retains its angular momentum. As gas accumulates, it settles into a rotationally supported disk, a flat structure where centrifugal force from rotation balances gravity's inward pull. This creates spiral galaxies. If gas has low angular momentum, or if it can't cool efficiently and settle into a disk, or if violent processes disrupt disk formation, the result is a spheroidal system, an elliptical galaxy. The key factors determining which path occurs are angular momentum content, gas cooling efficiency, the timing and violence of major mergers, and environment. Let's explore each path in detail. Spiral galaxy formation, the disk assembly path. Spiral galaxies form primarily through relatively gentle, gas-rich processes that preserve angular momentum and allow disk formation. The standard model for spiral galaxy formation is hierarchical assembly through cold flows. Dark matter halos form first, merging and growing over time. Gas flows along filaments in the cosmic web, long chains of matter connecting dense regions, channeling gas toward dark matter halos. In the early universe, when gas was denser, these flows could reach the central regions of dark matter halos relatively undisturbed. The gas is cold in the sense that it hasn't been shock heated to very high temperatures. This cold gas retains its angular momentum. As gas accumulates, it settles into a rotationally supported disk, a flat structure where centrifugal force from rotation balances gravity's inward pull. This creates spiral galaxies. If gas has low angular momentum, or if it can't cool efficiently and settle into a disk, or if violent processes disrupt disk formation, the result is a spheroidal system, an elliptical galaxy. The key factors determining which path occurs are angular momentum content, gas cooling efficiency, the timing and violence of major mergers, and environment. Let's explore each path in detail. Spiral galaxy formation, the disk assembly path. Spiral galaxies form primarily through relatively gentle, gas-rich processes that preserve angular momentum and allow disk formation. The standard model for spiral galaxy formation is hierarchical assembly through cold flows. Dark matter halos form first, merging and growing over time. Gas flows along filaments in the cosmic web, long chains of matter connecting dense regions, channeling gas toward dark matter halos. In the early universe, when gas was denser, these flows could reach the central regions of dark matter halos relatively undisturbed. The gas is cold in the sense that it hasn't been shock heated to very high temperatures. This cold gas retains its angular momentum. As gas accumulates, it settles into a rotationally supported disk, a flat structure where centrifugal force from rotation balances gravity's inward pull. This creates spiral galaxies. If gas has low angular momentum, or if it can't cool efficiently and settle into a disk, or if violent processes disrupt disk formation, the result is a spheroidal.
This ongoing accretion, often called the cold mode accretion, keeps spirals actively forming stars and maintains their blue colors and spiral structure. The disk is a dynamic, evolving system, not a static structure. Elliptical galaxy formation, the merger path. Elliptical galaxies form primarily through violent gas-pore processes that destroy disks and create spheroidal distributions. The leading formation mechanism for elliptical galaxies is major mergers, collisions between galaxies of comparable mass. When two spiral galaxies collide, their disks are disrupted. Gravitational forces stretch and deform the galaxies. Stars are flung onto chaotic orbits. The organized rotation of the disks is converted into random motions. Here's what happens during a major merger. First, the two galaxies approach and begin their first close passage. Tidal forces, gravitational gradients across each galaxy, stretch both galaxies, pulling out long tidal tails of stars and gas. The galaxies' shapes distort dramatically. After the first passage, the galaxies separate, but they remain gravitationally bound. They swing back toward each other for subsequent passages. Each passage further disrupts the galaxies, scattering stars and gas. Gas in the galaxies experiences different forces than stars. While stars interact only gravitationally, gas can collide. Gas clouds slam together, shocking and heating the gas to millions of degrees. This shock-heated gas radiates energy but can't easily cool to reform a disk. The compression of gas during the merger triggers intense star formation, a starburst. In a brief period, perhaps 100 million years, the merging galaxies might form stars at rates 10 to 100 times higher than normal. This rapidly converts gas into stars. Meanwhile, the galaxies gradually merge. Dynamical friction, gravitational drag from passing stars, causes the galaxies to lose orbital energy. Over hundreds of millions of years, the galaxies spiral together, eventually coalescing into a single remnant. The merger remnant is an elliptical galaxy. The disks have been destroyed. Stars orbit on random trajectories rather than organized circular paths. The system is supported by velocity dispersion, random stellar motions in all directions, rather than rotation. The merger also affects the central black holes. Each progenitor galaxy's central black hole sinks toward the merged galaxy's center. The black holes form a binary, emit gravitational waves, and eventually merge. During this process, gas funneled toward the center feeds the black holes, potentially triggering an active galactic nucleus phase. The intense starburst consumes most of the gas. Supernovae from massive stars heat and expel remaining gas. Feedback from the active galactic nucleus, powerful winds and jets from the accreting black holes, drives out additional gas. The result is a gas-poor system where star formation ceases. The newly formed elliptical galaxy is red, not because all its stars are old, but because it lacks young blue stars. The starburst created many stars that are now aging. Without ongoing star formation to create new blue stars, the galaxy reddens as its population ages. This merger scenario explains many elliptical galaxy properties. Their random stellar orbits reflect the violent formation. Their red colors reflect ceased star formation. Their correlation with dense environments, where mergers are more common, makes sense, and their old stellar populations formed during the merger starburst. Computer simulations of galaxy mergers confirm this picture. When two simulated spiral galaxies collide, the result looks remarkably like observed elliptical galaxies: spheroidal shape, red color, no disk, random stellar motions. The role of environment. Environment plays a crucial role in determining whether galaxies become spirals or ellipticals. In dense environments, galaxy clusters and rich groups, galaxies interact frequently. Close passages and collisions are common. Gas can be stripped from galaxies by ram pressure as they move through hot intracluster gas. Tidal interactions heat and puff up disks. These processes favor elliptical formation or transform spirals into lenticulars or even ellipticals. Galaxy clusters contain mostly ellipticals and lenticulars, with spirals being rare, especially in cluster cores. This morphology-density relation has been known since the 1980s. Denser environments have higher fractions of early-type galaxies, ellipticals and lenticulars, while lower-density environments have higher fractions of late-type galaxies, spirals. The processes driving this relation include galaxy harassment. In dense clusters, galaxies undergo frequent high-speed encounters with other galaxies. Each encounter heats the disk slightly. Cumulatively, these encounters puff up disks, transforming spirals into lenticulars or even ellipticals. Ram pressure stripping. As galaxies move through the hot gas filling galaxy clusters, they experience a headwind. This ram pressure can strip gas from the galaxy, particularly from the outer disk. Without gas, star formation ceases, and the galaxy transforms from a blue spiral to a red lenticular.
Strangulation. When a galaxy falls into a cluster, the hot halo of gas surrounding it can be stripped away by the cluster's environment. This cuts off the galaxy's gas supply. The galaxy can continue forming stars from its existing gas, but once that's exhausted, star formation stops. Over time, the galaxy reddens and transitions from spiral to lenticular. Major mergers. While mergers can occur anywhere, they might be enhanced in groups, environments dense enough for frequent interactions, but not so dense that galaxies move too quickly for mergers to occur efficiently. In contrast, field galaxies, those far from dense clusters, evolve more quietly. They accrete gas steadily, experience fewer disruptive interactions, and maintain spiral structures. This is why spirals dominate in low-density environments. However, environment isn't destiny. Some spirals exist in clusters, and some ellipticals exist in the field. The relationship is statistical, not absolute. A galaxy's history, whether it experienced a major merger, how much gas it retained, when it formed, also matters. The cosmic web structure also influences galaxy types. Galaxies along filaments, the chains connecting clusters, tend to be spirals. Galaxies at nodes, where filaments intersect, tend to be ellipticals. This reflects how matter flows through the cosmic web and where mergers are most common. Gas and star formation. The presence or absence of gas is central to understanding the spiral-elliptical dichotomy. Spirals are gas-rich. They contain substantial amounts of neutral hydrogen and molecular hydrogen, the raw materials for star formation. This gas resides in the disk, concentrated in giant molecular clouds where stars form. Typical spirals have gas fractions, gas mass divided by total baryonic mass, of 10 to 30% or more. This gas enables ongoing star formation. As gas clouds collapse, they form stars. Massive stars live briefly and explode as supernovae, enriching the gas with heavy elements and triggering new rounds of star formation. The cycle continues, maintaining the spiral's blue color and active appearance. Ellipticals are gas-poor. They contain little neutral or molecular hydrogen, typically less than 1% of the baryonic mass. Without gas, star formation is impossible. The galaxy dies in the sense that no new stars form. What happened to the gas? Several processes remove it. Consumption,
During the merger that formed the elliptical, intense star formation converted gas into stars rapidly. The starburst phase exhausted most of the available gas. Heating, supernovae explosions, especially from the starburst, heated remaining gas. Hot gas can be difficult to retain. If it reaches escape velocity, it leaves the galaxy entirely. Active galactic nucleus feedback, the central supermassive black hole, fed by gas funneled inward during the merger, becomes active. Powerful winds and jets from the AGN drive gas out of the galaxy. This feedback is thought to be crucial for preventing cooling flows in massive ellipticals. The result is that ellipticals become red and dead. Red from their old stellar populations, dead because they form no new stars. However, some ellipticals show recent star formation. These might have accreted gas-rich satellites or undergone gas-rich mergers. But this is the exception, not the rule. Most ellipticals are genuinely quiescent. The color magnitude diagram of galaxies shows a bimodality. Galaxies cluster into two groups: blue, star-forming galaxies, mostly spirals, and red, quiescent galaxies, mostly ellipticals and lenticulars. This bimodality reflects the underlying difference in gas content and star formation. Understanding what quenches star formation, what transforms blue galaxies into red galaxies, is a major question in galaxy evolution. The answer involves all the processes mentioned: gas consumption, AGN feedback, environmental effects, and mergers. Size and mass differences. Elliptical galaxies and spiral galaxies also differ systematically in size and mass distributions. Elliptical galaxies span an enormous range of sizes and masses. At the low end, dwarf ellipticals contain only millions or tens of millions of stars and span a few thousand light-years. At the high end, giant ellipticals contain trillions of stars and span hundreds of thousands of light-years. The most massive galaxies in the universe are ellipticals. Brightest cluster galaxies, the massive ellipticals at the centers of galaxy clusters, can exceed 10 trillion solar masses and span over 1 million light-years. These monsters formed through countless mergers over cosmic time, growing at the expense of smaller galaxies. Spiral galaxies have a more limited mass range. Most spirals have masses between 10 billion and 300 billion solar masses. Very low-mass spirals are rare. Below a certain mass, galaxies tend to be irregulars or dwarf ellipticals rather than organized spirals. Very high-mass spirals are also rare. The most massive systems are usually ellipticals. This mass difference reflects formation pathways. Ellipticals can grow without limit through mergers. Each merger adds mass. BCGs grow through cannibalism, consuming galaxies that wander too close to the cluster center.
Spirals, by contrast, are constrained. A major merger would destroy the disk, transforming the spiral into an elliptical or irregular. Spirals grow through minor mergers with much smaller galaxies and gas accretion, processes that don't destroy the disk. But this limits how massive they can become. There's also a fundamental plane for ellipticals, a tight relationship between size, velocity dispersion, and surface brightness. This relationship constrains elliptical galaxy properties and reflects their formation through violent relaxation, the process by which stellar orbits settle into equilibrium after a merger. Spirals follow different scaling relations: the Tully-Fisher relation connecting rotation velocity to luminosity, and the size-mass relation for disks. These relations differ from elliptical's fundamental plane, reflecting different structural support mechanisms: rotation versus velocity dispersion. Transformation processes. Galaxies aren't fixed in type. They can transform from spiral to elliptical or vice versa under certain conditions. The most direct transformation is spiral to elliptical through major mergers. When two spirals merge, the result is an elliptical. This transformation is irreversible in practice. Once the disks are destroyed and gas is expelled, the galaxy remains an elliptical. Simulations show that even gas-rich mergers between spirals typically produce ellipticals, though some gas-rich mergers at high redshift when gas fractions were higher might produce disk galaxies with thick, turbulent disks that could evolve into spirals. Spiral to lenticular transformation occurs through environmental processes. Ram pressure stripping, harassment, and strangulation remove gas and heat disks without completely destroying them. The result is a lenticular, a galaxy with a disk but no spiral arms and no star formation. This transformation is common in galaxy clusters. Many lenticulars and clusters were likely spirals that fell into the cluster and had their gas removed while their disks survived, producing the lenticular morphology. Can ellipticals become spirals? In principle, if an elliptical accretes large amounts of gas with high angular momentum, this gas could settle into a disk, potentially creating a spiral. However, this is rare. Most ellipticals are in environments where gas accretion is difficult, and the massive potential wells of giant ellipticals would make disk formation challenging. Some ellipticals show disky components. They're called disky ellipticals. These might represent ellipticals that have accreted some gas and formed a small disk, or they might represent specific merger geometries that preserved some rotational structure. Galaxy interactions short of major mergers can also affect morphology. Minor mergers, with mass ratios of 10:1 or higher, typically don't destroy spiral disks, but can heat them, trigger star formation, and build up bulges. Repeated minor mergers might gradually transform spirals into more bulge-dominated systems. Bars also play a role. Simulations suggest bars can drive secular evolution, gradual internal changes that build up bulges and redistribute angular momentum. Over billions of years, bars might transform late-type spirals, SC, into earlier-type spirals, SA, with larger bulges. Observational evidence. Multiple lines of evidence support our understanding of how elliptical and spiral galaxies form. Observations of galaxy mergers in progress show systems with disturbed morphologies, tidal tails, bridges of stars connecting galaxies, warped disks. Follow-up observations of merger remnants show elliptical-like morphologies, confirming that mergers produce ellipticals. The antennae galaxies are a famous example, two spirals in the process of merging, with long tidal tails and intense star formation in the overlap region. Simulations matching the observed geometry predict this merger will produce an elliptical. The morphology-density relation, ellipticals dominating clusters, spirals dominating the field, supports environmental effects on galaxy evolution. If environment didn't matter, we'd expect similar morphology distributions everywhere. The color magnitude diagram by modality, blue spiral sequences and red elliptical sequences, reflects the star formation dichotomy. The existence of green valley galaxies, intermediate colors between blue and red, suggests ongoing transition, consistent with transformations from star forming to quiescent. Stellar population studies reveal that elliptical galaxies contain old stars formed in intense bursts, consistent with merger-driven starbursts. Spirals contain mixed-age populations, consistent with extended star formation histories. Kinematics, how stars move, differ between types. Ellipticals show high velocity dispersion and little organized rotation. Spirals show ordered rotation. This matches predictions from formation scenarios. High redshift observations show that galaxy morphologies were different in the past. The universe at high redshift contained more irregulars and disturbed systems. Spirals were less common, and those that existed were often clumpy and turbulent. This supports hierarchical assembly. Galaxies were still forming and hadn't yet settled into modern morphologies. The number density of ellipticals increases with time, especially massive ellipticals. This supports the merger-driven formation scenario. Ellipticals build up through mergers occurring over cosmic time. Chemical abundances also provide clues. Ellipticals show alpha element enhancement, higher ratios of elements like oxygen and magnesium to iron. This indicates rapid star formation where core collapse supernovae, which produce alpha elements, dominated before Type 1a supernovae, which produce iron, had time to contribute. This matches the starburst scenario. Outstanding questions. Despite progress, questions remain about galaxy formation and the spiral-elliptical dichotomy. One puzzle is the diversity within each type. Not all ellipticals are identical. Some rotate significantly, others don't. Some are boxy, others disky. This diversity suggests multiple formation pathways, not a single simple scenario. Similarly, spirals show diversity. Grand design spirals with two prominent arms, flocculent spirals with many fragmented arms, different bulge-to-disk ratios, barred versus unbarred. What determines these variations? The role of supermassive black holes remains debated. AGN feedback is thought crucial for quenching massive ellipticals, but the details aren't fully understood. How exactly do black holes regulate galaxy growth? The abundance of intermediate mass ellipticals, those between dwarfs and giants, is difficult to explain with mergers alone. Do they form from different processes than giant ellipticals? The relation between black hole mass and galaxy properties, the M-sigma relation, is remarkably tight. How did black holes and galaxies co-evolve to produce this correlation? Observations at higher redshift probing earlier cosmic times continue to reveal surprises. Some massive galaxies appear to be already quiescent when the universe was less than 2 billion years old. How did they form and quench so quickly? The detailed mass assembly histories of galaxies, how much mass came from mergers versus star formation, when major growth occurred, remain uncertain for most galaxies. Future observations tracking individual galaxies' evolution over time will help constrain these histories. Closing. Understanding elliptical versus spiral galaxy formation reveals fundamental processes shaping cosmic structure. Spirals form through relatively gentle processes preserving angular momentum. Gas settles into rotating disks. Cold flows channel material along filaments. Star formation proceeds steadily over billions of years. Disks build up gradually. The result is flat, rotating systems with ongoing star formation, blue, gas-rich spirals. Ellipticals form through violent processes destroying disks. Major mergers scramble stellar orbits. Starbursts consume gas rapidly. AGN feedback expels remaining gas. The result is spheroidal, non-rotating systems with ceased star formation, red gas-poor ellipticals. Environment matters. Dense clusters promote elliptical formation through mergers, harassment, and gas stripping. Low-density fields allow spiral survival and growth. Transformations occur. Spirals can become lenticulars or ellipticals, though the reverse is rare. The dichotomy isn't absolute. Lenticulars bridge the gap. Some ellipticals have disks. Some spirals have large bulges. Diversity exists within types, but the fundamental distinction remains. Disks versus spheroids, star-forming versus quiescent, gas-rich versus gas-poor. This understanding comes from decades of observations, theory, and simulations. Every deep image revealing galaxy morphologies, every spectrum measuring stellar populations, every simulation modeling galaxy evolution contributes to the picture. The story continues to unfold. Future telescopes observing galaxies at higher redshift will reveal how morphologies emerged in the early universe. Improved simulations will test formation scenarios in finer detail. New observations will uncover exceptions and refine our understanding. But the basic framework is established. Ellipticals and spirals represent different evolutionary pathways from similar initial conditions, shaped by gas physics, angular momentum, mergers, environment, and time. Understanding their formation helps us understand how the universe evolved from uniform plasma to the rich diversity of galactic structures we observe today. Thank you for exploring galaxy formation with me. If you found this valuable, subscribe for more deep dives into cosmic structure and evolution, and leave a comment. If you could watch a galaxy form in fast forward, would you choose to watch a spiral or an elliptical, and why? Keep questioning, keep observing, and keep marveling at the universe's architectural diversity.